Is ammonia just a fertilizer, or is it the key to unlocking the global hydrogen economy? You've probably heard that hydrogen is the future of clean energy. But storing and transporting it, that is a real challenge. Today, in our A to Z of Hydrogen series, we are diving into A for ammonia, what it is, how it's made, and why it's getting so much attention as a hydrogen carrier, and whether it could be the solution to hydrogen storage and transport challenges. Let's get into it. Welcome to TT Talks Energy, where we break down complex energy topics into engaging, easy to understand insights. Let's start with the basics. Ammonia, or NH3, is a compound that's made up of one nitrogen atom and three hydrogen atoms. It is produced using the well-established Haber-Bosch process, which reacts nitrogen from the atmosphere with hydrogen over a catalyst at high pressure and temperature. Ammonia is colorless, but it has a strong smell and is mostly used in agriculture. About 80% of global ammonia production goes into fertilizers. In fact, it has played a crucial role in feeding the world for over a century, helping to support nearly half of the global population's food needs. Beyond fertilizers, ammonia is also used in refrigerants, plastics, and various industrial applications. But in recent years, it's gaining attention for another reason: its potential to store and transport hydrogen efficiently. Currently, the hydrogen used to produce ammonia comes mostly from fossil fuels through a process known as steam methane reforming, making ammonia production responsible for about 1.8% of global CO2 emissions, and that is the highest of any chemical industrial process. This means that decarbonizing ammonia production itself is a big opportunity. But ammonia's emerging value in the hydrogen economy comes from its physical properties, which make it an attractive carrier for storing and transporting hydrogen. Let's break that down a bit. So number one, ammonia liquefies at minus 33 degrees centigrade or under pressure around 10 bar, while hydrogen requires extreme cryogenic conditions at minus 253 degrees C. This makes ammonia significantly easier, less energy intensive, and cheaper to store and handle than liquid hydrogen. Ammonia has an energy density of 12.7 megajoules per liter compared to liquid hydrogen's 8.5 megajoules per liter, and that means around 50% more energy per unit volume. This means that ammonia can transport more energy using the same storage space. Existing transport infrastructure. Ammonia is already widely transported using pipelines, ships, and storage tanks. And in contrast, hydrogen requires specialized infrastructure, which is costly, requires specialist materials, and is under development at the moment. The potential for direct use. Ammonia can be used directly in gas turbines, fuel cells, and internal combustion engines, reducing the need for hydrogen conversion. I'll give two examples here. First of all, a South Korean shipbuilder is partnering with Baker Hughes to develop ammonia-fueled ships using their gas turbine technology. The second example is the Viking Energy vessel, which is set to become the world's first offshore platform supply vessel to sail long-distance emission-free using 2 megawatt ammonia-powered fuel cells. The International Maritime Organization has committed to reducing greenhouse gas emissions from international shipping by at least 50% compared to their 2008 levels by 2050, and ammonia is set to play a key role as a green fuel for shipping. Lower energy losses. Liquid hydrogen suffers from boil-off losses of about 0.5 to 5 volume percent per day due to its low boiling point. Ammonia, in contrast, is more stable with a much lower boil-off rate of 0.025 volume percent per day, making it more viable for long-distance transport. So this all sounds promising, right? However, it's not without its challenges. Despite its benefits, ammonia isn't a perfect solution, and this is why some experts are skeptical about the use of ammonia. The energy conversion losses. Converting hydrogen into ammonia and back into hydrogen involves around 30 to 40% energy losses. This makes it less efficient than directly transporting hydrogen, especially for applications that require pure hydrogen. This is because ammonia cracking, which is essentially splitting it back into hydrogen and nitrogen, requires high temperatures to produce high yields of hydrogen. In addition, ammonia is toxic and corrosive and it requires strict handling regulations. It can cause respiratory issues, skin burns, and environmental damage in the case of leaks. So large-scale ammonia infrastructure would need enhanced safety protocols for new energy applications, lack of end-use infrastructure. And while hydrogen fuel cells are advancing, ammonia burning engines and fuel cells are still in early development, and retrofitting existing power plants and ships for ammonia combustion could be costly and technically challenging. So with all these factors in mind, what is the verdict? Can ammonia truly be the answer to hydrogen storage and transport challenges? There's a huge opportunity to decarbonize the ammonia production process by replacing fossil fuel-derived hydrogen with green hydrogen. Ammonia provides a practical and scalable solution for hydrogen storage and long-distance transport, leveraging existing global infrastructure. However, its energy conversion inefficiencies and potential safety risks means that it's not a one-size-fits-all solution. So we need to carefully select applications in which we use ammonia, and we need to make sure that stronger safety measures are in place. As we make advances in ammonia cracking technology, this could improve its viability as a hydrogen carrier. Around the world, ammonia is gaining traction in the decarbonization of various industries. For example, we have Japan's Mitsubishi UBE Cement Corporation, who recently tested ammonia co-combustion at a cement plant. And in Australia, ammonia-based hydrogen refueling technology for fuel cell vehicles is in commercial development. Now, I want to hear from you. Should the world invest in ammonia as the key to hydrogen transport and storage, or should we focus on other solutions? And in which scenarios have you seen ammonia being used to enhance the decarbonization agenda? If you found this breakdown useful, don't forget to like, subscribe, and hit the notification bell for more videos in the A to Z of hydrogen series. Next up, we have B for hydrogen backbone. Can a continental pipeline network unlock a true hydrogen economy? Join me as we explore the infrastructure needed to make hydrogen a global energy carrier. See you next time on TT Talks Energy.